Yeah. Okay. Uh, right. Uh, Let us see. I don't know. It's okay. So I would to answer this question, I don't know the answer. I okay. My first guess, if you want, I would say yes. Okay, but that's just a vague guess. But I would like to think the following: is Rn a free group, or rather, is it a free abelian group? So before we think about this, the reason why I'm asking this is the following. So there is a fact which, let's state that first. So if you have a free group like this, then so there is a unique free group up to cardinality of I. So if two free groups are isomorphic, then they have the same cardinality of the I, and also if you're given the cardinality of I, then there is a unique free group, free abelian group. Okay. So this fact, and which maybe we can assume for now. Yes, right. And I think the answer is no. It is not a free group, but let me think. Maybe simpler question is Q a free abelian group? Q certainly has no torsion. If that is probably not important here. We know that it's not finitely generated, but is it free? So question is, can you write Q as a direct sum of copies of Z? Yeah, and the answer is no, because if suppose it was possible, you have some generators. So let's say that these two are, so there is a generating set. Let's say these two are in the generating set, right? But a non-trivial combination will give you zero, right? Non-trivial integer combination, right? So the answer is no. And obviously this answer is also no. So then this answer is no, and no, no, no. Sorry. So let me be careful. It's not so obvious. Is R right? That's right. But it is right. Yeah. Yes, exactly. You can. It's free. Over Q, it is free because it's a vector space. So R is, but that might lead to something. So R is a direct sum of copies of Q. And when I write this, uh, do I have to say something? Yes, as Q vector spaces. Yeah. Um, right. As Q vector spaces. Otherwise, this expression doesn't make sense. So as Q vector spaces means I cannot say as groups anymore. So oh no, I can scroll. Yeah. Okay. So R is free over Q, and but Q is not free over Z. So I would like to say that then R is not free over Z, something like that. Yes. Well, so for finitely generated things, it is like if you have a free group, free abelian group, then any subgroup is also free. But for, yeah, for, is that true for infinitely generated groups? I do not know if subgroup of free is free if it's infinitely generated. What can one do in this kind of question? In this direct sum for copies of, okay, Okay. Right. Yeah. But with integer coefficients. Mm. Okay. Right. So you're trying to construct. That's interesting. So s- looking at the polynomial ring as an abelian group, then you want a subgroup. So you take the ideal generated by X. This is a subgroup. Yeah, I mean, it's a finitely generated ideal, but it's not a finitely generated group, right? As a subgroup, it's not finitely generated. Yeah. Yeah, but we are interested in whether it is free. Uh, yeah, this is a very strange but interesting. Yeah, x square. Yes, this is certainly free because it is nothing but, yes, this is free because it is just this, right? And but it would be more interesting if I considered some arbitrary polynomial and then took the ideal generated. So when I multiply, yeah, then it's, so if I take this to be x plus 1, for example, then this is like, so this is like what? So it contains things like 1, 1, and hence n times. So it contains these kind of things, and of course, many more things. So we don't even have an example where it becomes free, where it becomes not free. So, so is there some different reason to say that R is not free? Hmm. I don't know, no. Let's see. If if uh, if Rn is isomorphic to Rm as groups, so which means same thing as Z modules. So there is an isomorphism. So that is an isomorphism as Z modules. Then from here, can I construct an isomorphism as R modules? That will give us a contradiction, right? So I'm just changing the approach because should see if we can solve the question. Huh? Yes, exactly. That is what I was trying to think. Yes, yes. They are, yeah, so that's what I was going to say. So they are isomorphic as Q vector spaces, right? Actually, so you wanted to say if you can conclude from there, but they are already isomorphic as Q vector spaces. And so just restrict that isomorphism and you get that they are isomorphic as Z modules, right? But let's just write it so that we can see if there is any mistake because so we know that they are isomorphic as Q vector spaces. So phi is Q, and this is because the cardinality of the basis is the same, and that is vector space theory. Because that's what you said that they are free as Q vector spaces. So we saw that. So we have this. So this is isomorphism, but then this isomorphism we just restrict. It is an isomorphism of Z. I mean, if there is an isomorphism of Q vector spaces, then it's obviously an isomorphism of groups also. So yes. So the answer is yes. Answer is yes. Yes. Yeah. It's quite easy when we see it. But so I was looking at the wrong things actually. Yeah. I mean, this was, anyways, yeah. That's, but still, I mean, I would like to know if R is a free abelian group, right? If R is a free abelian group. You see, that might still not be correct. I mean, if this was not isomorphic, then I could have said that they are not, that R is not a free abelian group. Because if R is a free abelian group, then the answer is yes. Because then again by cardinality. But answer is yes. but again, it doesn't mean that it's a free abelian group. So is R free over Z? Like we can see that there is no torsion, but that is not any, that's not a, Q also has no torsion, but Q is not free. Yes, Z is free abelian group. Yes, because if it was, then there would be some generators, but which would generate it freely. But these generators cannot be free because these two have a non-trivial linear relation, Z relation, because the relation is this. This is zero. Yeah. So with the usual module structure, the usual group structure, it is not free. So it has no torsion, yet it is not free. But it is an injective Z module, if you know the types, or you can try to think about it. It's quite interesting. It's an injective module. So it's not free, but it still has some properties of a free module, which is, but we should try to answer this question. Is R a free? Direct sum? It is a, yeah, it is a direct sum of copies of Q. So it is free over Q and Q is not free over Z. Yeah, I don't know. Yeah, that's good. Hmm. Of Z and try to get a contradiction. Yes, yes, it should work maybe. So let's see. So if R is generated as alpha I in I, Right. Then uh, as over Z, which is of course the same thing as R is a direct sum of, but then this, but then we also know that R is a direct sum of Qs. And we can assume that this J is contained in I because this alpha i's would be a generating set for that for R as a Q vector space also. So you can take a basis, a subset of it, which will be a basis. So that is something which we can always do. Now, right. So now it should not be difficult. No, but we have to think about Q over Z. Yeah, this doesn't give me, this doesn't tell me how to go from Q to Z, or doesn't. Yeah. So like if you fix some beta I, then you have that Q beta I, and that is isomorphic to Q, but it's not necessarily true that from the Z alpha i's you can get to Q, that Q. So it is like, I think, I don't know, I think we should try to construct a counterexample where subgroup of free is not free. Because if that is true, then this is then we can say the answer is no, right? Because Q is a subgroup. And for infinitely generated modules, Don't know if subgroup group is free. Like you were trying for polynomials. I don't know what kind of techniques are needed. It's just we should just think about this for a sec. Subgroup of free. So we have this. Yeah. Just think about it. Have some water. It's quite hot here. The ZX could have any kind of subgroups. We don't know because it is just this direct sum of Z. And yeah, in that case, yeah, yes. Why? Yes, it's not true. Yeah. Yeah, I don't. Maybe I would think that we take those polynomials. uh, we take some polynomials and see if this ideal is free or not, right? We couldn't check it. That is the problem. And this cannot be a very difficult question. That is the thing. Because, yeah, sort of a. One has to decide like which is the correct way. Should we check these? You check these, then it. So the zero is there and the multiplicative. हाँ कुछ बोलियो. Yeah, I think it is worth revisiting why is subgroup of a finitely generated group is free, right? Without using the structure theorem. I mean, does it come in the way of proving the? Does it come up while proving the structure theorem? Because we need to see what is the role of finite generation there, right? So right, so there is a general fact, right, that submodule, or maybe I just say that R be a PID, that R be a PID, right? And if N is inside M is free, then N is free. So of course, finitely generated, then N is free and it has strictly fewer generators. That's also a fact. But how does one prove this, and what is the role of finite generation in that? Yes, it should not work everywhere that submodule of free module is free, because we can take some examples. So if you take polynomial ring in two variables, it should not be true, because you take yeah, it's not true because you take a if you take like this two variable. Now if you take this, then this is a ideal that is generated by a single thing, and this is free as a module over kx comma y. Uh, Correct, right? It is free because just so this, yeah. So I just say that this ideal is free over this generated by x, right? Cyclic things. It's free. There is no torsion, so there are no relations. So this is fine. But of course, you can take submodules which are not free because you can take, okay, maybe you can, yeah, you can take x square and xy, right? This take the submodule generated. This is contained in this and it is strictly contained in this, I suppose. But it is not free because again, you can just take some combinations. Yeah, this is not free because whenever you have two things, you can always just multiply by the other one and get zero. It's probably a unnecessarily complicated example. I would say that, yeah, I mean, I think you already observed maybe that if some R is not a PID, then this will not be true, more or less. I mean, unless, yeah, you can, because basically that's all I use, right? If there are two generators, if there is a, yeah, I think you get it. If R is, try to prove that if R is not a PID, yeah, you can just take R itself is free over R, but you take a sub ideal which is generated by two things, it's not going to be free. So that's a unnecessarily. Uh, yeah, 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 but it won't have less number of generators necessarily, right? Yeah, it's that's true. I mean, then yeah, then you're right. So every submodule of finitely generated module is finitely generated, of course. Yes, that's correct. That's correct because Noetherian condition sort of forces that. It's a hereditary condition in that sense for modules. Uh, uh, I mean, yeah. So why is it why is submodule finitely generated? Because yeah, because submodule is Noetherian. Yeah, and Noetherian is finitely generated, right? So the Noetherian condition is that hereditary whatever condition because it's built into the definition. Sub ring of a Noetherian ring is not Noetherian, but submodule of a Noetherian, yeah, yeah, because the Noetherian condition is on modules, is on ideals, is not on subrings. So all that is easy, fine, but right. But how do you show that M is free? How do you show that N is free? Hmm, submodule. Yeah, this is of course a standard result, but we should just think maybe. So let's say that, and it of course follows from the structure theorem, but it should be proved before the structure theorem usually. One should be able to prove it. So let's say that Hmm. Okay. Okay. There has to be a way to project the vectors, these MIs themselves, to N. There has to be a way to project the vectors. Then we will eventually get that P0, but also in this way you may not actually, because take minimal or something. So take a minimal generating set. No, I don't know. Maybe you can think about it and maybe tell me. Yeah, maybe you should tell me this proof next time. How this is done. I am not able to do it. Yeah. So tell me that next time. But so yeah, here also we are unable to do this thing about this. Because then if you try to prove it or you try to see the proof, you may realize if finite generation is needed or not. Yeah, we don't have any techniques beyond this, it seems. That is a problem. Yeah. Yeah. Which fact? I mean free? Yes, that's right. But I want you to see how to prove that for even for finite generation. Try to look at the proof, right? Because there you may find if you will realize if it's necessary or not when you do the proof, right? Because I don't know any examples where, yeah, don't know. So still I feel there should be a simpler proof of this R is free over. Like you said that we could use this vector space thing. Where to go down? But how to use it, I don't know. So this Q is a R. No, this doesn't. So like, I mean, one thing we know that if you take a tower of free things, then it will be free. That kind of thing. So if you have these are all rings, so we can state it in the generality of rings. You have something like this, and if this is free and this is free, then you can say that this is free, right? Then R1 to R3 or rather, yeah, this is free. And this is going to simply uh, eh, but we have to also see that these are the rings, but these are also modules. Then only you can talk about these things. So these are also a chain of modules. Can we prove this? This should be easy. This should not be difficult. And then what we want to prove is more than this, that if any two of these three things are free, then the third one is free or something like that, right? Yeah. Yeah, but that I believe that should not be true. And proving that would be difficult. Yeah. Yeah. So first, we have to try to prove this one. This should be easy. And the next thing is like 2 out of 3 kind of thing. So if you have, uh, yeah, but this actually is not a good question, I believe, because the other question is a special case of this. But still, you have this, and you have this, right? So 1, 2, 3, right? So if any two are free, let's say free extensions, then so is the third. Okay. Yes, right. Yeah. And also the other third combination, the three possibilities. So if beta I over R is a basis, free over R2 is a basis, and alpha j over R1 is a basis, then if you want to generate, what do you think? Do you think this beta I alpha j would be a basis? Yes, right? This should be a basis. It's certainly a generator, but why is it a basis? That we have to see, because right, that is true, right? Because oh no, wait. So hmm, hmm, hmm. So if you have some 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 Cij beta I alpha j, some obviously finite combination. If some finite combination is equal to zero, if some finite combination is equal to zero, right? Because then you will have this. Yeah. Yeah, this and you know that these are also not zero. If none of those two are zero, the product is not zero because beta I was free. So yes, yeah, yes. So it's free and it's a generator. Yeah, so that works. But we just used. Yeah, we also we are in a way using. Yeah, no, it's a bit more. I mean, the proof is incomplete, but you can, but if you but you can complete it if you have not already understood. Yeah, it's a bit incomplete, but you have to use the full power of the fact that beta I is also a basis. Or maybe I've done it the other way. Actually, I've done it the other way. I should do the alpha here and the beta here. But you can prove that this is the basis. Yeah, this is. But you have to use the full force that beta and alpha are respectively their basis. So this is easy. So at least there is something. So tower will be a free thing, which is expected. But yeah, the other one you check, right? Try to prove it and then tell me and see if you can resolve the question, right? Yeah, maybe that is what. Yeah. Yes. Yes. That's all I would say. Yeah. Yeah. So we ended up discussing this. Now, if you say, I don't know if this is anything new, but is what it is if it's a fun problem. Yeah, this offshoot of the problem is more difficult for us. We were able to resolve the original question, but yeah, s- some techniques are there which we are not able to imagine. Yeah, think of yes. So that was just the cardinality thing. Right? That so this fact better to write. You can write like this that yeah, that this is isomorphic to this if, of course, if the cardinality is same, right? So if the cardinality of I and j are equal, then these two are isomorphic. We did not even prove this, but you can try to see if you. But I don't think there is much to prove. I think you can prove it. Yeah, it's easy. Yes, and these kind of things are present in many places. You would see that like So basically, the class of object is determined just by cardinality of some underlying thing. Just like for vector spaces, and this is true here. It's also true in more enriched objects, like if you have something called a Hilbert space. So basically, just an infinite dimensional thing with an inner product. Okay, where vector spaces over R and C have inner product. So if you take infinite dimensional vector space with an inner product, and of course and to bind it some uh, completeness condition, the vector inner product defines a topology. It should be metric. It should be complete, and so on and so on. Then you get something called what is called a Hilbert space, and there also it's true that if you have two Hilbert spaces, um, so yeah, if you have two Hilbert spaces and they're vector spaces, so if their vector space basis has the same cardinality, then the Hilbert spaces are also isomorphic. So that's more than just isomorphism as vector spaces, because the vector spaces are isomorphic is already true from linear algebra. Just like here also you can prove, but that is more. Even as Hilbert spaces, they are isomorphic. However, but there actually it's very critical because there the inner product is used. But if you just take a vector space with a norm, not coming from an inner product, an inner product, then cardinality, then isomorphism as vector spaces, which means equality of cardinality of basis may not imply equality, may not imply isomorphism of the as topological spaces. So basically, there is the inner product, where inner product ensures there's orthonormal basis, and that really is a game changing. Here also, I don't know some techniques we are missing. There is a projection technique. I know it's there in Dummett and Foot. I have obviously studied it at one point, but it's not coming right now. I have to think more peacefully. There's some projections, some family of maps, and something, but I have to think. Meanwhile, you should also think and try to see. Okay. Yeah. So yeah, this is